Okay, I think we got everything set up. We're going to mainly talk about some generative design today. So that'll be the main topic. I've got a couple of other little things scattered around, but the main thing is generative design, particularly in Fusion 360. We did topology optimization in SolidWorks. I don't know, maybe 2 weeks ago or a while ago. We previously did a little overview of topology optimization. So both of they're similar things. They are different, and they have slightly different goals and different work processes, workflows, but they're kind of getting at the same idea of you've got some constraints of some sort on a design that you're trying to do the CAD model for, and then eventually create the product or the part, and you want to take advantage of computer simulations in order to optimize that design in some way. So they both take that general approach. They come at it from different directions. So in general, a topology optimization. So this is the one that we did previously. We did this in SolidWorks. It runs locally on your computer that's running SolidWorks, and it is taking a design that you have created. Maybe it's a really rough thing, but you've got some geometry there, and it is optimizing. So it's topology optimization. So it is taking whatever you built and basically eating it away towards some goal. So the goal might be to make it as light as possible while maintain some strength or some rigidity. Don't maybe it's a factor of safety against the material failure, von Mises stress, or something like that. So typically, it starts with this block of material that you've modeled that sort of represents. It's got mounting holes, it's got load application points, it's got interfaces. It might have some things you have to keep, like you have to keep a certain surface here, you have to avoid something there. It's got these constraints on it, and then it will iteratively use finite element analysis to solve that load configuration and eat away the material, basically. It kind of bounds the initial space. So whatever that block was that you started with is the envelope that the final product, the topology optimized part, will end up in. And so that works pretty well. I think we made a shelf bracket is what we made out of it. I actually don't remember if that's what we made or not. That's usually what I do as an example, is some kind of little shelf bracket looking thing. And it eats away at it. Now, both of these, topology optimization and generative design, the resulting thing from the computer usually has to go as kind of a template or a model or inspiration for somebody to go back in and actually do the design work based on what the solution looked like. You can, in both of them, you can take the final mesh, maybe smooth it out a little bit, and then just print that. So you could do that. But generally the idea is that you're taking that as inspiration for something that you will go and design a little bit more traditionally, just to make things not quite as random in the final design. So that's topology optimization. Generative design it's trying to do the same type of thing, but it takes a little bit different approach, and it typically, although it's not 100%, but it typically runs in the cloud, because of one feature of generative design is that you are going to get a lot of options. So in industry, you might have 10,000 options that it's going to explore. But here you sort of start out in the same thing. You don't model a block of material to eat away at, but you do have to model some constraints, some obstacles, some preserved regions, things like that. So you have to put in some something for it to work on. What kind of load is it going to deal with? What sort of are there obstacles it has to avoid? It can't generate material in that space. Maybe there's a bolt hole that has to be preserved, something like that, some access hole, or it's got to go around something. What kind of loads is it going to have to endure? So it has that. And then it will. Oh, and then there's probably some goals constraints also. Are you trying to lightweight? Are you trying to use a particular process? Are you trying to do a CNC process, a molding process, an additive process? What kind of materials are you going to use? So you give it these kind of constraints that define the workspace, and then you send it off, usually to the cloud. Although I know that there's one that we'll do locally in Topology. We'll look at it later, sometime later in the quarter. But most of them, since you're trying to generate many options, you're a single PC at home or in your office. It's probably not going to be able to do that in a reasonable amount of time. So you usually send it to the cloud. Fusion 360 uses AWS, the Amazon service, or I think it uses Amazon Cloud, whatever it's called. I think it's AWS. Anyway, it uses a service of cloud computing to send your ideas to, and then it will process them out in the cloud and bring back some number to you, whatever you've asked for. Again, typically you're looking at several options, but in some cases you might be looking at thousands of options. And even the ones that you get back from Fusion 360 from their cloud service, each option has many stages that you get. So you might have 20 or 40 stages per option you got back. Then it's kind of a slider. We'll look at it later. And you can kind of see the process develop of where it started and where it ended up at. It gives you a lot more kind of, I guess, I don't know if it's a lot more freedom, but it is less constrained than the optimization route. So the optimization route, you give it a starting part and then it eats away at it. The generative, you give it a set of constraints, it generates a starting part and starts eating away at it. So it ends up looking very similar, but it is a little more free on the front end. Basically, it's generating a lot of these options that it's trying to work on. So both of these processes in general are set up in a way that the idea is you're probably going to use some kind of metal 3D printing or a nylon, like a laser sintering type thing, something where it doesn't, you're taking advantage of the freeform creation. So you've got, unlimited fabrication options there. You've got a strong material, like metal or even the nylon for a laser sintering powder-based machine type of thing. FDM is a little bit different. You can do this for FDM prints. You lose some of the reasons to do it for FDM print. There's still some reasons, and I'll look at I made a list over here that we'll look at in a second. But a lot of the reasons you could just make a rigid, lightweight bracket. If we're thinking of shelf brackets, you could go the topology optimization route, or you could go the generative route and end up with this, spider web looking bracket, and it's lighter weight and everything. But when you're thinking of FDM printing, all those little spider web parts might be kind of hard to print. They might be simpler to just take the triangle that defines the bracket and put 3 or 4 walls and minimal infill, and you've got the same strength, maybe even lighter weight, and much faster print time. So it doesn't always make sense in FDM printing, but I did come up with these rules. Let me share them here. Oh, well, let me fix the thing so that you can share them. There we go. Now you can see them. So I put down this list. These are the things I could think of. There's probably others. These are the things I could think of. So what about generative? Oh, and here's a list. This is all in Canvas, so you can look at it later if you want to. This is basically the generative design versus topology optimization, how they're different but still kind of similar. Here are things why you still might want to do generative design or topology optimization. So I talking about generative design most of the day, but this would apply to generative or the topology optimization. So one thing, and in FDM printing. So you're not metal printing. You're not laser sintering or anything like that. You're just doing an FDM printer, and you want to see why you might want to use generative design. So you do have load direction optimization. So parts that are FDM printed are highly dependent on which direction you're loading them. They're not, they don't have isotropic material properties, because you've got these layer lines that are typically much weaker if you're loading in shear along the layer versus compression or well, compression certainly, and then their tensile strength is different across the layer. So you might have some luck in mitigating that with generative design. Heat dissipation. So not necessarily of the part itself, but if you've got this brackets inside a piece of electronics, and you're relying on some airflow to cool the electronics, and it's this big block of a bracket, now you're blocking a lot of that airflow. But it could be that if you did a generative design, FDM print it, the holes that are all in the design will not block the airflow, so you get some actual airflow in there. Same thing with water flow. If it's in water, maybe it probably creates some turbulence, but it wouldn't create as much turbulence as if it's just a solid block in this path. So there could be some flow reasons, not for the part itself, but for whatever the part, airflow or water flow that the part is in itself. Obviously, just aesthetic. Maybe your product isn't a structural thing. It does have some structural requirements, but it's really an ornamental thing. And so then it makes sense, because you do get a much more interesting looking part with your generative design or topology optimization versus the block that you started with. It's sort of related to the number one here, but the unique material mechanical properties. I'm thinking a little bit different here, but you could manipulate maybe the flexibility of the part itself. So if you ever look up meta materials in 3D printing, we might add that in at some point. Sometimes I'll talk about it, but the idea that a solidly printed part can have compliance. So another keyword, if you're interested, is compliant mechanisms. Compliance in certain directions based on the geometry. And so you can create particular deformation patterns that might be useful. Maybe it's a toggle, or maybe there's some reason that you want it to deform in a certain way versus other ways when it's loaded. I'm thinking this could be with PLA. PLA is not great at cycling in deformation. It'll break pretty quickly. But nylon can be 3D printed, and it is a pretty good, can cycle 20 or 50 times. Or some of the actual flexibles. TPU is coming to mind as a part that you could very easily manipulate the way it's going to deform when you put loads on it. And so you could also put some topology optimization. That would be I don't know if Fusion 360 would be the right way to do that particular thing. It probably is, and I probably just haven't delved that deep into topology they do generative design with Fusion 360. But if you could almost manipulate what it's trying to do when in the generative design, then you could control the motion of the part as it deforms. And then you still get the benefit of learning about the process. So you still can do the generative design and topology optimization, print them on your FDM printer, and get an idea of what the limits are and what the advantages are, so that later on maybe you can print this in metal or print it in a nylon laser sintering type part. And that is still good to do. So it's an exploration, educational type of thing. So I did come up with, there are reasons to do this in the context of FDM printing. Let's look at an example. So there are Airbus uses a lot of generative design in their A320s, and This is obviously not an Airbus. This is a motorcycle that we're looking at right now. This is just a picture of, this is from formlabs.com. And this is kind of their overview. I did link this here. I think it's the Generative Design overview, that link. So this is just kind of one result of what you might get. We're going to look at an example from Airbus because they actually did this, and they've done it in several. They did a seat bracket, I think. They're trying to, build airplanes, and they want as light of weight as possible, because every little bit of weight that you can save is less fuel. It's more efficient on the airplane, using the airplane. But this is just a picture of what a generative design could look like. So there's another picture here. Here's kind of a, let's see if I can make this fit on the screen. Yeah, there we go. We'll leave that alone for now. Here's kind of a workflow. The designer is still in the loop. You don't just turn these things on and let them go and then grab the output and go take it to a printer. You still have some initial idea of what are the constraints that you're trying to meet. You might have some rule algorithms that go into this. In this case, what we're going to do, the rule algorithms are going to be also part of the constraints, I guess. They're calling the initial idea maybe that I need a bracket, or I need a partition, I need a thing, whatever. And then the rule algorithms are going to be these constraints that we'll put in place. Source code, we're not going to manipulate the source code at all in here. The designer you may have some of that. In fact, the Airbus example that we'll look at does have some of that in it. And then there's a n number of solutions generated. The designer judges those, maybe adjusts the constraints, maybe there's some iteration there. And then even then, after they pick one of these, they still probably, the design team has to go and take that and then manipulate it in a meaningful way to make it usable. So it's not just a completely random design. Here's a little difference between topology optimization and generative design. It does mention that the role of the engineer does change a little bit. Here, the engineer is probably up here in the design box, also giving input to these rule algorithms and source code, and evaluating the solutions versus just drawing lines and extrusions and revolves and cutaways and that kind of thing, bevels and fillets and all that. So there are slightly different roles that the engineer might play. Also, another reason why using FDM printers as an educational tool, because you have access to that much easier. A 3D metal printer is significantly more expensive than the FDM printers that we're using. The larger scale metal printers are, $250,000, $500,000, and those are the smaller ones. Now you can get into the laser sintering nylon powder. You can get into that. I don't think I would call it a consumer level printer, but it's not a large industry either. You could be a small industry, get into nylon prints that are laser sintered and solid prints, and you really don't have the weakness across the layer line type of things. It is there, it is potentially there, but it's not the same as it is an FDM printer. So, and that's reasonable if you're a small business. I don't think a person, unless you just have a lot of money, a person will have one of those as a consumer, but they're not terribly expensive either. Here's some brackets. Here's the left-hand side is what the engineer might think of, and it works. But now your goal is lightweighting so that you can lightweighting and automating. So not only are you lightweighting the part by removing material, but you're automating the process by putting it on a printer. There's still post-processing, still some handwork that has to be done. But, this part has some welding that has to be done and some aligning, fixturing, jigging, that kind of stuff. So you might even be speeding up the manufacturing side a little bit, possibly. the printing is still slow. Probably you could make the by hand part faster, I would think. Then you could make the lightweight generative part. And then over here, they've even minimized it further, removing a lot of the material. Let's see. There are some benefits to it. Simultaneous, that's another piece that you're sending this part idea to the cloud, and it's working on it on a print or a computer farm somewhere, well, a cloud somewhere, and it's generating many ideas all simultaneously. Now, you're probably paying for that. Fusion 360, if you're an academic license user, I think you still get unlimited credits for that sort of thing. But an industrial user, then you're going to have to pay for that cloud service. As part of that simultaneous, you are accelerating the design timeline. You can be specific on what type of process you want to manufacture. You could still say that, hey, I only want to CNC and weld, so I don't want to 3D print. So don't give me designs that have to be 3D printed. Give me stuff that I can make out of flat material, flat stock, and I can CNC it or laser cut it or whatever, water jet. And so you can control that. I don't want to be too fancy. These are the machines I have available. Can you use a generative process that is constrained to water jet cutting or 2D, cutting? Here's a list of some of the different software packages. Fusion 360 is the one we'll look at today because it does have a free license for users. I don't know if you're a free user who's not an .edu. I don't know if you can do the generative part, at least not for free. So I'm not sure about that. If you have a education license for Fusion 360, I'm pretty sure you can still do free generative design. Creo, we don't have that one, or I don't have that one, so I can't look at that one. In Topology or InTop, this one, I think it runs locally, so it doesn't do the quite as big of an exploration. And I don't know if I would call it generative design or not. I'd have to look. I think it's more of a topology optimization thing. We will look at it later in the quarter, and I'll see if it has generative design. But what I remember, it was topology optimization. It even has topology in the name of the thing. NX, that's another CAD program. I don't have access to that right now. Apex. So there's some others out there that also have this. The one that we'll look at is Fusion 360. Here's just why it goes together. Now, this is Formlabs. They have a consumer-ish level, at least small industry level, laser-based resin printing, small desktop printer is their main product. And, you can get their smaller ones in the $4,000 range, I believe. And so this does kind of apply to them. But you are doing resin printing. It's not laser sintering. It is laser, but it's laser polymerization, not sintering. Let's see. Well, here's some of their parts. I assume that's theirs if it's on their website. So you can kind of see. Well, you can't really get an idea of the generative part there. I guess if we watch the video, we could. But you can kind of see what they're doing. There is. Oh, you know what they're doing here? This is castable material, I assume. So there are resins. I don't see where they're saying here. But there are resins that are castable in a lost wax casting type of approach. So they printed a master, and then they ran it through lost wax casting. So you encase it in plaster, melt out the wax, then pour in metal, molten metal. And it looks like they did not print these metal parts, but they are, let's see, the end result combines metal 3D printing. Okay, maybe they did. Maybe they just used these as examples. There are some processes that you can print metal filaments and metal infused parts and then sinter them down to remove the plastic that's part of them. I don't think that's what they did here, though. I actually would have thought they cast these, but I don't know. I didn't read their whole article. Here's a frame. much smaller than it looks in the pictures up here. But here's the little frame. This is clearly they're going to sandcast. They've got their sandcast set up here. And then looks like they cast it in aluminum. There must have been the original one that had some, manual type of light weighting. And then here's the generative version. It weighs 40% less. You can actually buy. So it's like these are New Balance, but New Balance, Adidas, or Nike, they all have shoes that have some level of directly printed parts on them. Usually it's the lower part. There are some that are completely 3D printed. I don't know if those big brands or that. I think that's an offshoot brand that's the 3D printed shoe entirely 3D printed. But you can kind of see where they've got this generative design in the sole for cushioning and that sort of thing. So let's look at this example. So this is on Autodesk's site, but it's about the company Airbus. And I linked all of these links are here if you want to go look at them. This first link is an actual paper, so like a research paper. It is where did that find it? Is this it? No, it's this one. So let's see if we can get it all on the screen. If you want to find a research paper about related to the Airbus project that we're talking about, relatively recent, 2019, actually published 2020, then you could look for this. It is a free download of the PDF of it. So I assume it's an open source journal, Journal of Laser Applications. But this is a whole paper on the whole process. So we won't go through that entirely in its details, but you can kind of get an idea of the research side of this process. All right. So what they wanted to do, let's see if I can find. All right, yeah, this is a good picture. So back here, there's a partition, and they want to create a lighter weight. Their whole goal has been to create an efficiency in their airplane. They have a I don't know what level this person is, but somewhere I saw a quote from an Airbus official that in the future we want to make the plane completely renewable. They put it in a way that you could eat the entire plane. So they want to make it out of biopolymers or whatever. They want to make it completely renewable. But that's not what they're doing right here. Right here, they're just trying to make it more efficient. And so there's this partition back here between the passengers and the crew. And they want to lightweight that panel. But they want to maintain the strength and everything. And so they go through, here's their design constraints. Has to be significantly lighter than what they're already using. Has to be strong enough because 2 flight attendants' seats are going to be anchored to it. So it has some strength characteristics that it has to maintain. Has to have a hole in it where you can pass items back and forth, like food trays or whatever. 1 inch thick is the maximum width for this panel. So they do have some geometric constraints other than it has to fit in the curvature of the plane. And only attach in 4 places. Not sure what that goal is about, but maybe that's the way the current one attaches, and so they got to use those same attachment points. I don't know. And then they took 2, so they are calling this bio-inspired optimization. I don't remember their exact phrase, but it's something along those lines. And they took 2 biology, so things from life, patterns that they want to implement in the design, because biology has had many iterations in order to optimize solutions for particular problems that they have. So this one is based, like where the struts go, it's based on a slime mold, which has a very efficient way of connecting points together. And so they have the pattern that gets generated based on a slime mold trace, like a slime mold path that it would take. And then the actual individual struts, each one, let's see if I can get that all on the screen, is based on the mammal bones. So bones aren't solid. They have, particularly like the larger end, the greater trochanter region of your femur, the inside of that is very hollow. And they have a shell around them that does most of the work. And then there's a hollow-ish structure inside. And so they want to take that inspiration and create the actual struts based on something from mammal bone. So they took these two nature-inspired ideas, coded them. So remember, sometimes the design is in the coding itself. So they coded those as ways to go about generating the solution. And they call it the bionic partition because they're taking cues from nature. And they end up, here's some examples of, these are the different things that the slime mold pattern suggested as places to put the struts. And they're running them through a finite element of just where the stress is going to be great and small, that kind of thing. And so you can kind of see, obviously, the more struts there are, the lower the stress is. Fewer struts, you got really high stress. And so they're somewhere in the middle. I don't know which one they ended up choosing. They've got, here's some of the parts that they actually printed. They've got these joints, and this is several parts stacked adjacent to one another. They've got, here's just some of the initial ideas of what they were thinking, just written out on paper. So that's that idea block of, hey, we want to do something like this. Let's see, this is you can kind of see the laser dot over here. So the way these laser printers work, all this grayish white stuff is powdered metal. They have their own special blend of metal that's specific for airframes at Airbus. So whatever their alloy is, it's ground into super tiny little particles and laid out on a surface. And then the laser goes around and heats up those particles to their melting point so that it fuses them together. And then another super thin layer of powder is deposited over the top. It's kind of like got a wiper that wipes a new layer of powder across it, and then the laser comes back and welds another layer on top. So it's built up layer by layer still. Here's their actual assembled version. So that's what I don't know if this is the one that ends up in the plane or if it's just like the first prototype. But you can kind of see the cutout for the window that can go and pass objects between the different sides of the partition, and you can kind of see the scale of what they're printing here. Now, and again, they printed this, all these little joints here are so that they could print it in multiple pieces. They don't have a single printer that could print this in one go in metal. Here's just a picture of how the joints work. They're screwed together with kind of like a turnbuckle. There's just some of the results. They're estimating that just this one part, being lighter weight, will save 3,000 kilograms of fuel per partition per year. So based on every partition they install and the amount of flights that Airbus is going to take, they're saving 3,000 kilograms of fuel. They've got a CO2 emission reduction, 95% less raw material that they're using. In this process, there is no waste. All the unused, unfused powder is filtered and sifted basically and used again. So you don't have any waste unless there is a little bit of support material. Let's see if they had supports in here. I don't know. There might be some supports mixed in with that. Looks like maybe right in that area might be a support. I'm not sure. But they generally just use the powder itself as the support because it's still there. It's just not hardened, not fused. So I think there is very minimal waste of supports. It can have supports, but it's minimal. Let's see. All right. So then here I found this article. Did they actually ever use this thing? So in 2021, they have actually installed these partitions. So I never found a picture of one of the partitions installed in a real Airbus. I mean, I guess you could see this panel, but not the actual partition itself. The structure itself, the panels covering up what you actually see or what you want to see. But it does say that they installed these in, I don't know if they ever gave a date of when they installed them. At least I didn't find it. find it. But they did actually install these and are, as far as I know, still using them in the A320S. Along with other parts too. They have seat brackets and other parts that they've done the similar process on. So that's kind of generative design overview. Let's try and do some of our, now we aren't going to be able to do the generative design and get our solution today because it is a lengthy process of the actual processing the design and getting your results back. But I've already done one and we will look at how it works. So let's look at this. So I'm over in Fusion 360. I have the education license, so I do have access, or at least I did. I haven't checked today. I have access to generative design tools for free. Or, well, you can do the generative design tools. It's the actual design part that you may not have for free. So here we're making our shelf bracket. So it does not at all look like a shelf bracket, but let's go over into the generative design pull down here and see what it looks like. All right, so I've got some different colors now. So across the top is kind of where you define your constraints. So you've got areas you want to preserve. So maybe there are specific locations you have to have this because it's a mounting point, or maybe you just want it there or whatever. So there's some feature that you don't want it to change. So you want that to stay. There are some places that could be obstacles where you don't want it to go. So there's that surface needs to be flat, or maybe that there's a pipe that goes through there and it can't, your object has to go around that or whatever. You could design a starting shape. Then it starts to look a little bit more like the topology optimization because you're letting it define the starting shape. But you don't have to do that. So you can leave that part out and let it just generate what it wants to as a starting shape. Sometimes it's good to have symmetry. I don't think I did symmetry on this one. Maybe we can add symmetry and see. Maybe I'll check and see. I see symmetry planes over there. I just don't know if I added one or not. But you could have left and right or top and bottom symmetry if you wanted to. You can have multiple symmetry planes. So maybe you're doing a quarter model and you want it to have multiple symmetries just to speed up the process. You can also, on those obstacles, you can say, hey, maybe the way I did it is I just drew the obstacle itself, but maybe you've got an assembly and there's a part that it has to go around. You define that as an obstacle, but then you say, I don't even want it to kind of get close to that. So you go in and assign an offset. Hey, you have to stay this far away from obstacles. So that's kind of that process. You can edit the model, but what I did is I just went into the design tab and built the model as several different pieces. Over here, there can be structural constraints. So maybe there's pins and rollers and things that you have that attach this to whatever. You can apply. You probably should apply some kind of load condition so that it knows where to try and mitigate that load that you've applied to it. You could have several load cases. You could have mass. Here are some objectives. Let's click on that one. So there are two primary. They're over there. You can see them. There are two primary. Just make it as light as possible while maintaining a factor of safety, or make it as stiff as possible while maintaining a factor of safety and trying to get to a certain mass. Now, it can't be 0, but you can also define a displacement. So, it can only deform a certain amount. I did not define one on this one. I think I left it blank. But you could just say, and that's related to the stiffness, but in a different way. So you could be more specific on, instead of just some stiffness idea, you could just say, it cannot deflect more than this distance. And you could either globally, like anywhere, or at a specific location. So you'd have to select the location that can't deform. All right. Also in here is manufacturing. So you can include a cost estimation if you have that set up. I think it pulls from a database. if you don't have your own cost estimation set up. You could just say, just give me anything you can think of. So you could do that. I only selected the additive processes, and then it says, well, which way do you want to print it? Is it going to be printed this way, or laying down flat? What way are you going to print the thing? I selected 2 orientations for printing that I thought would be good. Or you could just say, hey, just tumble it in there any way it can go and let it fall where it does. You kind of give it an idea of how steep your overhangs can be that maybe you don't want to include support at all. And so you can tell it, hey, don't give me any overhangs in any of these orientations that I selected that are more than 45 degrees, because I know my printer can print 45 degree overhangs with no support. And so it can help with creating a part that not only is optimized for lightweight and rigidity, but it's printable without supports, which might also be another factor you're considering. You can tell it a minimum thickness so that it never gets any really thin parts, because most printing processes at some point are going to break down when you try to print too thin. Oh, in fact, the resin printing we did last time, I posted in Discord that I'd found a model of a V8 Chevy engine from 1967, I think, 327 maybe, and it's a little thing. Actually, let's look at it. Let's look at it over here. So here's the block itself, and the model I found was a 1/3 scale model, and then I reduced it 25% of that, so I'm down to like a 1/8 model or whatever, and it's pretty small. The thing is that this actually printed pretty well. So there's a lot. I mean, you have the holes for the lifters. You have water passages in there. I think every detail, actually, you have bolt holes that are showing up in there for the head bolts. So you got a lot of detail, but I don't even have one. Here's one of the heads, so you can kind of just see what you can get on the resin prints. This isn't even the lowest. This is 50 microns. You can go down to 10 microns. I looked it up on that Mono X from Photon Anycubic. It'll go down to 10 microns. So you could go even thinner deep layers, but the problem was the intake manifold. I don't have one here, but the intake manifold was so thin that the orientation I had, it was thinner than the minimum layer thickness that I was doing. So it just didn't print those parts because they didn't exist as far as it was concerned. So you can say that, hey, I know that my printer is gonna need at least some thickness, and here it's set to 3 millimeters, which is fine. You can usually get away on FDM printers with 1 millimeter. But if those 1 millimeter are like 1 millimeter diameter rods that, part of your spider web, then that's probably too thin for it to print reliably. So you could do that. You can also say that, well, what if I just want to do a milling process? And so you can say, hey, I want to do 3-axis milling, 2.5, 5. I've got a robotic arm mill, so I could do 5-axis milling. 2.5 is what you're thinking of a lot of times, where it's just it's mounted in a fixture and you're milling from one direction. 3-axis is, you've got another axis that's either like a trunnion or something that lets you move the part around. Maybe it's just a can't think of the name now, but it lets you rotate the part. So you can define that, hey, I want to do milling, but I'm going to restrain it to these different things. How big is the tool? It'll tell you how long is the tool. And so it'll tell you how far it can get in there, and it will create parts that will fit in that constraint. You can say 2-axis cutting. So I want to cut this part on a water jet or a plasma table or a laser table, or a little vinyl cutter even, although that would just be one very thin layer. And it'll limit what its solutions look like to stuff that can be 2D cut. And then die casting. Whoops. So apparently this is a preview of die casting, but die casting is similar to sand casting, except you reuse the die. So Hot Wheels used to be die cast. Maybe they still are. The metal bodies are anyway, I think. I assume they are because they make a bunch of them and they wouldn't all be sand cast. But they are metal. So I assume they're die cast, which means that you can reuse the mold for it. And so if I'm die casting, then I have to have things like draft. I have to have some angles on the parts as I pull the mold apart so that the actual part comes out. So, and there's some thicknesses and all that kind of stuff on the minimum feature size type of stuff. So the only one I clicked on was additive. But you can add all of these. It sends all of that information to the cloud, and then you will get back your solutions, your potential solutions. So let's look at what I have. So in preserved geometry is green, so you can kind of, it's color coded. I turn them off there. So I need a top and a back because I'm making a little shelf bracket. And so the top has to be a certain location to put the shelf on, and the back has to be something I can mount to the wall. I used all of these, actually everything else I guess, as obstacles. So I did not want any material to grow up above the top of the shelf. I wanted it flat, so I just put a box up there and say, hey, don't grow any material up there. I guess technically it could find a way to grow around there, but I don't think it would. And I've got to mount this shelf to the wall, so I don't want any material going back this way because otherwise it's not going to mount smoothly to the wall. I put these little cylinders, the little ones, kind of in the middle here, put those there to don't grow any material here, and I probably should have moved them, all the way out. I don't remember what the solutions looked like, but what the idea was there is that, hey, I've got to put a screw in here to screw it to the wall, so I need a way for the screwdriver to get in there and the screw. So thinking about it now, looking at it, these probably needed to go way out here so it didn't put any geometry in the path of them. I did not do an obstacle offset, did not give it a starting shape. There's no geometry that's unassigned, not doing anything. Looks like I did not use a symmetry plane on this one, although a symmetry plane right down through the middle would have probably been good. That would have made sense to have left and right look similar. The objectives I gave were to minimize mass and to target a factor of safety of 2. I think those are the default ones, actually. And we just looked at, I only did an additive process. Now, I chose 2 materials. So in the materials over here, it does not have, or it didn't. Let me check and see what it has now. It's loading. It didn't have materials like PLA. These processes that it assumes you're using are the laser-based, sintering-based type of processes, not FDM printing. And so it has all of these. These are all materials that are typical in the metal 3D printing world. Plastic Labs Fuse 1. I don't know that one. That's a PA, so that's a nylon. There's a nylon. Lots of nylons. Those are laser sinter powder of nylon that's melted together. This is Peak. Oh no, not Peak. This is Peck. I don't know that one. So that's with carbon fibers. So the EOS P810 printer can do that one. So they don't have one that is like PLA. I did add just ABS plastic as close as I could get. So the strength characteristics may not be exactly what it's thinking of. Let's see what load case I gave it. Oh, so I gave it a constraint back here that this doesn't move, and a point load, or no, it looks like a distributed load across that top of the green bar, which was the top of my shelf. And I told it, let's see. Oh, well, it has gravity, so that's gravity. So that's what that yellow arrow was. And I gave it a force of, so what did I tell it? 100 newtons. So it had to hold 100 newton load spread out over the top up there. Okay, and then I constrained, you can see that little lock back there. I constrained the back of that plate, saying that that can't move anywhere. Then I sent it away. So I did the generate pre-check. It was fine. I think we can actually do a preview. The preview runs locally, and it'll give you maybe a step or two of what it's going to think about doing. I don't think that takes terribly long, although it's not doing anything right now. I'll give it a sec. Oh, okay, there we go. So you can kind of see it. There's its starting shape that it's thinking. It has to go around that obstacle, and it can't go. It has to keep the green. It can't go in the red. So right now it's just kind of that there's a hole there, but it doesn't go all the way through. That's why I was thinking that that one probably needs to be longer. So, you know, it gives you an idea of the general direction it's going to take. You can actually make, yeah, you can do higher details. We won't do that though. Then you do generate. Then once you've sent it off, it will actually, let's do that so you can see the process. That's fine. All right, so here, and it says account education required. This would normally how many credits that it's going to take to, actually the cloud credits would be up here, I think, or maybe this dash right here. Available, unlimited. Oh, it won't let me do it again because it didn't change anything. It's already solved it. So you would click what study you wanted to generate, and it would show you how many credits it's going to cost and how many you have. Right now I have unlimited, so I think all of the education, I don't think it's just the teacher education. I think student education still get unlimited. And then you would submit it or generate it, and it would do this. So now that I've already run that, we can explore the results. So these are the 8 results I got back. All of these converged. Remember, converged means that it is a finite element solution process, and it is iterative. And what it means for converged is that the solution that it generated didn't explode. It didn't like take off exponentially or oscillate back and forth infinitely or anything like that. So the solution did converge. That's generally a good thing. It doesn't mean it's necessarily correct. It just means that it at least didn't have obvious errors. And you can kind of see, actually, I think all of these might be the same. Yeah, these look the same. These are probably the 2 different materials. Probably one of these is ABS and one of these is the steel, I assume. Let's just select one and see what it looks like. So this is our ABS in the X positive orientation. So printing with X up. Let's see, that would be this way. So printing this way, except probably we could look at it better. Oh, no, not that way. Oh, how do we get X to go up? And now I want to go, oh, there we go, printing that way. So it does look like that shows X up. I think it's showing X up. Yeah. I don't think it considered my 45-degree overhang right in that location. I'm not sure. That's definitely doesn't look like 45 degrees, but I don't know. Maybe I'm misinterpreting what it's thinking of as X up, although that's the X-axis pointing up. So I don't know. But there's a interesting idea. It did turn out that my obstacle here was not long enough, so I could not actually very easily get a screw to go in there. In fact, it filled in some of that hole, so I needed, apparently that little cylinder was not formed correctly. It needed to go all the way through. The bottom one worked fine, so I didn't have that preserve region quite the way it should have been. Let's see. And also along the bottom here, you can see it did 23 iterations. I can slide through and let's go back a couple of iterations. Here's what it was thinking in the middle. So very similar, but not quite the same. Let's go back to even further. there's kind of what we had in the preview window, you know, sort of like that. And you can kind of see where, I'm not sure why it's adding those bumps, because there is a obstacle there. So that's, well, it's not done at that point. It does get rid of them eventually, although that one's still there. I must have something weird in that location where that little short cylinder was, because it's not acting right. And then you can create a design from this outcome. You can create a mesh directly from here. I don't know if that's also in the cloud. Yeah, that's going to be a cloud solution also. So it does look like it's a free cloud solution. It's not charging me for it, or it's not saying it's going to charge for it. So what it's doing is taking this, whatever kind of geometry this is, and turning it into a mesh that I could then go and manipulate. Looks like I can display a stress view. So if I want to see where the stresses are, green is ideal, blue is low. I don't see any red anywhere. Oh, well, not sure why. I must have some kind of odd thing in my setup, because there shouldn't be any red stress on those edges. We could check another one. So this one, I think that was this one up here. It's also working on that one. I'm not sure why. Let's see, where are my materials? Let's turn off the ABS ones. So let's look at the aluminum ones. Looks very similar. It did change the material property in the renderer, so it looks shiny. Now this one did a slightly better job on maintaining that hole, but it's still not, so there's something wrong with that obstacle. I'll have to check and see what's going on with that. Gives me some stress. You know, there's hardly any stress on this at all, because now it's aluminum with 100 newtons on it. It gives me a mass. It weighs 0.021 kilograms, so not very much. Only 13 megapascals of stress, which is a factor of safety of like 100 nearly, or maybe it is 100. Oh no, it says minimum factor of safety of 18, so somewhere in there. But so in finite element analyses, you do have to be careful, because if your mesh has these little sharp points in it somewhere, then that can create a really high stress concentration in the calculations that's not actually there. It's just a function of like a sharp corner in the mesh, and so don't just trust those blindly. You do have to know a little bit more about what the mesh actually looks like. I wonder if I can even see the mesh. No, not in here anyway. So that's kind of how this generative process would work. Getting these does take a while, but they don't take up your computer. They just run, and still preparing our mesh. I think we can probably look at job status here. Oh, no, not that. I don't know where it's going to give me my mesh that I asked for. It may just download it. I'm not sure where it's actually going to put the mesh. It might be tied to this one whenever it actually completes it. So we'll look at that maybe sometime if I remember to go back and check on it whenever it's done. So it's a pretty cool process. It's useful. It can be used in FDM printing, although you lose some of the benefits of it. You know, the printing process itself, it might actually take longer to print one of these parts FDM versus a laser style printer. So if you have a resin printer, then they will be faster parts. Resin prints are typically solid anyway, so it might be, you know, useful for resin printing. You do have to be considerate that resin printing is typically pretty brittle at the consumer level until you add in some of the tough resin or a little flexible resin or something like that. The standard resin is pretty brittle on its own. These little parts are not like going to break, but if they had tiny details, let's see if we can get close to some of their details so you can see what we did print. I don't know. There's a coffee cup. how close we can get to them. Put them in different orientations and see if we can zoom down on them. So you can kind of see what you're looking at with this was on that 50 microns on the Anycubic Photon Mono X 4K, so the older one. They have higher resolutions now. This is just some regular old resin. This is the resin, aqua blue from Anycubic, so it is their own resin. 500 milliliters in there. It's super easy to sand. Resin, you do have to be careful about the dust that you're generating when you sand, because breathing the dust would be harmful. Touching these after they're cured is not a problem. Touching the liquid resin can irritate your skin, and eventually a repeated exposure will give you chemical burns, potentially. And so you can kind of see, you get some really good details. Let's see if I have here's some centimeters, so you can kind of get an idea of how the size of these things. So the whole thing's 40 millimeters long. So some of those details are sub-millimeter level details in there. And again, even that resin printer can go much smaller on the layer thickness. It is limited on the pixel size. It is a 4K screen that's, what did we say, 8 or 9 inches wide, 7 or 8 inches wide, I don't remember now. But they are higher resolution screens out there. All right. I think that's a good overview. You can do a generative design as one of your optional assignments. I think you can even do it as your final, what I call it, technical memo. You can do a topology optimization or a generative design discussion as write up as your technical memo, and then print the part. And it doesn't have to perform quite as expected, because unless you have access to the right kind of printers, then it's going to be a FDM printing part, which is going to, the solutions don't consider FDM prints. They don't consider the layer lines of a FDM print as part of the material properties. I have not tried building a custom material that had anisotropic properties. Maybe that's possible. Maybe somebody's tried to do that. I'll at some point probably look that up, or at some point somebody will get that working in these finite element solutions. I just don't know about it currently. All right, we'll see you on, it'll be Friday,